Undergraduate engineering programs provide students a great deal of theoretical knowledge, but the constraints of the academic environment make it difficult to comprehend certain problems and challenges faced in industry. One key challenge is the possibility of a design failure. Since the probability of failure increases with the system's complexity, engineers must purposefully incorporate contingency plans. However, it is difficult for inexperienced students to accept the need for backup systems. Only by designing, building, and testing real-world systems do they truly grasp that a well-designed system includes contingency designs that will allow it to continue operation even when a subsystem fails. My name is Nicolaisen, a recent graduate of Cedarville University's Mechanical Engineering program. Through my senior capstone design project with the Cedarville University's Solar Boat team, I learned the necessity of contingency plans. I developed an energy management system, or EMS, for a solar-powered boat entered in the Dong Energy Solar Challenge, referred to as the DSC. Throughout the design, I considered all possible modes of failure and introduced backup systems to ensure that the boat could still operate if individual components failed. After spending a year working on the project, we competed in the DSC in July 2012. During the race, we had various failures, yet we still finished the race and won third place in the top class using our contingency plans. The Dong Energy Solar Challenge is a solar boat race that takes place in the Netherlands. The race consists of two broad categories, the challenge class and the top class. Out of these categories, the top class has broader design constraints, and the competitors must supply their own solar cells, providing a more competitive and challenging event. The race follows the route of the Elfstedentocht, the 11 cities ice skating race held in Friesland province, and covers 220 kilometers over 5 days of racing. It includes such challenges as low bridges, shallow canals, and stretches of open water. While Cedarville has competed in solar racing competitions since 1992, entering the DSC top class in 2012 required us to design and build a new hull, electronic system, solar panels, maximum power point trackers, or MPPTs, and an EMS. Our design work was governed by a power budget in order to operate the system efficiently. The power budget shows the cumulative effect of component losses and the diminishing amount of power available to propel the boat. Complex interactions between boat speed, solar energy input, wind and wave effects on drag, drive system efficiency, battery characteristics, and the overarching goal of finishing each leg as quickly as possible required a sophisticated energy management system. We needed to develop an EMS that could monitor energy use throughout the system and determine the optimal boat speed throughout the day. The major hardware components of the EMS are shown on the slide. EMS software runs on a microcontroller that reads the incoming signals, runs an optimization algorithm, and outputs the desired speed or energy usage requirement. It reads and writes signals from many of the subsystems in the boat: the batteries, MPPTs, the signal conditioning card, SD card, GPS, and LCD. The program determines the distance remaining in the race, estimates the energy that is available, and determines the speed that will use all the remaining energy just as the boat reaches the finish. This will be the shortest possible time and thus the fastest possible speed for our system. The code was developed because this type of real-time calculation is beyond the ability of the driver, who must focus on navigating the boat. The most difficult part of the algorithm was establishing communication with all of the devices and providing seamless integration with the rest of the system. We faced numerous problems as we designed and developed the electronic system, but the two most serious problems we faced were communications issues between systems and recurring malfunctions of several components. We could not determine whether the malfunctions were due to errors in our circuit or due to manufacturing defects. It became evident, however, that the scope and complexity of the required EMS was monumental, and our ongoing difficulties made clear the necessity of incorporating contingency plans into the design. We focused on the EMS and each component that interfaces with it, and came up with plans so that in the event of any component failure, we could still send or receive the data necessary to operate the boat successfully. The process of considering all possible failure modes has the natural consequence of recognizing criticality of certain information and functions. From there, it's often a short step to find a contingency, an alternative way to achieve the same result. For example, we purchased 2 pre-programmed commercial LCDs that connected directly to the battery charge controllers. They provided redundant information during normal operation, but in the event we lost communication with the battery management system, they would still provide vital battery information, such as energy remaining and important error messages. These plans certainly weren't optimal, but they would work in case of a system failure. Because we were working under such a short time constraint, after identifying problem areas and developing contingency plans, it still remains that there wasn't enough time to thoroughly build and test each scenario and contingency in the plan. So the question became a matter of priorities. Should we strive to work out the bugs and build a solid design in the remaining time, one that would have a lower risk of failure and less likelihood of needing a contingency plan? Or do we stop revisiting and improving the incomplete design and focus on developing a robust series of contingency plans because we are absolutely going to need them? Our ultimate goal was not to have a perfect EMS that met all of our design goals, but rather it was the much broader goal of winning the competition. There are 2 types of contingency plans, external and internal. External contingency plans account for malfunctions outside of the specific system. Looking at the EMS, for instance, all the contingency plans we had in place were focused on external problems, such as lost communication with other systems. Our plans in this regard were fairly sound. Without realizing it, though, we neglected to develop contingency plans for problems internal to the actual EMS algorithm. Such internal contingency plans would take into consideration internal failures in how the software implements the EMS functions. Our fatal flaw, discovered on the day before the race, involved a defective subroutine. While we were able to pinpoint the problem, the complexity of the code prevented us from disabling the faulty portion of the code without interfering with the rest of the software. We were forced to abandon our original plan and resort to our backup design. With the onboard microcontroller unable to perform the EMS functions, we resorted to our most basic plan, manual energy management and speed determination. The new algorithm was very minimalistic. It read the raw values we needed from each critical subsystem, sent them to the LCD, and stored them on the SD card. We created an Excel spreadsheet that would calculate everything the microcontroller was designed to do in order to give us a single value, in this case battery current, for the driver to control. We had already put so much work into the logic of the EMS algorithm that it was a quick and easy process to translate this to another application. We had made provisions for the driver to communicate with other team members via a hands-free Bluetooth mobile phone headset. So we built on that and established an energy management team that would receive status updates on critical information at regular intervals via cell phone. Then we would run the calculations with a laptop computer and then communicate back to the driver the optimal current draw for the motor for that point in the race. The race was spread out over the course of a week, giving us time to identify and fix flaws in the new system. Overall, however, the system seemed to be working. A great benefit of reverting to such a simplistic approach was that it allowed the EMS team, who had designed and programmed the algorithm, to understand what would have been going on behind the scenes during a racing scenario. By mentally and tactically being in the loop as part of the EMS process, we were able to find areas where the algorithm could be greatly simplified. Despite the crudeness of our new EMS system, we effectively drained our batteries on all but the shortest legs of the race. We had been concerned about other teams with intricate EMS systems, developed by electronic specialists that incorporated CAN buses for data acquisition, Wi-Fi network connections, and much more detailed code structures that could handle large amounts of data. But they weren't without problems. One of our top competitors lost connection with their boat during the race, and without an onboard backup system, they had difficulty completing that leg of the race. Our team ended up taking 3rd place in the top class overall, and finishing as the top university team in the competition. We had spent nearly a year designing and building our energy management system. It proved greatly beneficial that the team understood the physics of the energy management problem, and had spent as much time as we did considering how our system could fail in developing contingency plans. Some might argue that if we had focused more attention on making the system work instead of diverting time to our contingency plans, we wouldn't have needed those plans. Yet we correctly reasoned that the probability of running into some sort of failure was too high to ignore. This was especially true when you consider what was at stake if a failure did occur. By working on the EMS and spending time developing contingency plans, and ultimately relying upon them, we learned valuable lessons in engineering design and how to keep the system running despite failures that will inevitably occur. This was a lesson that could not merely be taught in a classroom, but one that could only be learned through a design project, such as our experience working on the Cedarville University Solar Boat team.